Hi everyone, it's Professor Primton. In this video we're going to talk about how to find the absolute maximum and minimum of a function on an open interval. So in the previous video we talked about how to find the absolute maximum and minimum of a function using the extreme value theorem on a closed interval, because on a closed interval we know that we have an absolute maximum and an absolute minimum value guaranteed. In this video we're going to talk about how to find the absolute maximum and absolute minimum of a function, but on an open interval. So let's pick up where we left off. We're going to review how to use the extreme value theorem to find the absolute maximum and absolute minimum of a function, but on a closed interval first. So example 4, finding absolute extrema, find the absolute maximum and absolute minimum values of the function f of x equals 10 times x times the quantity 2 subtract natural log of x on the following closed interval for 1 comma e squared. Notice that we have a figure of the graph of the function here, but we're not actually going to use it to find the absolute maximum and absolute minimum. We're going to use calculus methods with the extreme value theorem. So let's review what we did in the previous example. We know that we have an absolute maximum and an absolute minimum because we are talking about a closed interval for this function. So x equals 1 and x equals e squared are included as part of this interval. So let's find out what the y values are at the endpoints. You have one endpoint at x equals 1. If you plug this into the original function to find out the y value, you have 10 times 1 times the quantity, 2 subtract natural log of 1. Natural log of 1 is 0, so this is 10 times 1 times 2 minus 0, or 20. So the y value is 20 at x equals 1. Now that's not an absolute minimum or an absolute maximum until we check all the y values for the endpoints and the critical numbers. So let's check the other endpoint. If x equals e squared on the right endpoint, if you plug this into the original function, you'll have 10 times e squared times the quantity 2 subtract natural log of e squared. Since natural log of e squared is just 2, then this becomes 10 times e squared times 2 minus 2, which will be 10 times e squared times 0, which is just 0. So the y value is 0 at the right endpoint, x equals e squared. We know that we're going to have an absolute maximum and absolute minimum, but it may not occur at an endpoint. It may also occur at a critical number. So now the next step is to find all the critical numbers of the function f of x by finding the derivative f prime of x and determining where is the derivative 0 or where is the derivative undefined. So let's find the derivative f prime of x first. Notice that you have to use the product rule because you have 10 times x times the quantity 2 subtract natural log of x. It's a product of two different functions. So one function is 10 times x, take the derivative of the other function, the second function, d dx of 2 subtract natural log of x, plus, because it's the product rule, now keep the second function the same, 2 subtract natural log of x, times the derivative of the first function. So d dx of the first function is 10 times x. Now let's find out the derivative of the first function and the second function. So you have 10 times x times the derivative of the second function. Derivative 2 is 0. The derivative of negative natural log of x is negative 1 over x. Keep the plus sign. And now the second function is 2 subtract natural log of x. So now the derivative of the first function, the derivative of 10x is just 10. So now you have 10 times 2 subtract natural log of x that you have to distribute the 10 through the parentheses to actually simplify. So 10 times x times negative 1 over x, the x's will cancel out, and so you'll have just negative 10. And now the 10 distributed to the parentheses, you'll have 10 times 2 is 20. And then 10 times negative natural log of x will give you negative 10 natural log of x. So if you combine like terms, you'll have 20 subtract 10 is 10. And the other term is negative 10 natural log of x. Notice that there's a 10 in common with both terms, so they can be factored out as the greatest common factor, or GCF. So you have 10 times the quantity. You have 1 from the first term left over after you factor out the 10, and the second term you have natural log of x. So the derivative f prime of x is 10 times the quantity, 1 subtract natural log of x. So let's find out where the derivative is undefined. Notice that you do not have any x's in the denominator of a fraction, so you will not have division by 0, but we do have a natural log of x in the derivative. The natural log of x is only defined whenever x's are greater than 0. So the derivative will be undefined if the x values are less than or equal to 0, which is good because in our case, the closed interval that we're concerned with is only from x equals 1 to x equals e squared. The x values will not be less than 0 or equal to 0 for our closed interval that we're concerned with for finding the absolute maximum and absolute minimum of the function. However, the derivative could be 0, so f prime of x equals 0 gives you an equation to solve for x. You have 10 times the quantity, 1 subtract natural log of x equals 0. Well, 10 can't be 0, so you have 1 minus natural log of x equals 0. And if you solve for x, you have natural log of x equals 1. What value of natural log gives you 1? Well, the natural logarithm is log base e. So you have log base e of e is 1. So that means x must be e. That's a critical number for the function. So now the next step, we know that we could have an absolute maximum or an absolute minimum at a critical number. So plug x equals e back into the original function to find out the y value. If you plug x equals e into the derivative, you'll get 0. That's what we just found out. So if you plug e back into the original function, you'll have f of e equals 10 times e, because it was 10 times x, times 2 subtract natural log of e, because it was 2 subtract natural log of x. And if you simplify, you'll have 10 times e on the outside of the parentheses, Natural log of e we just talked about is 1, so you have 2 minus 1 inside the parentheses. So 10 times e times 1 will give you 10 times e. That's the y value whenever x equals e. So now that we have all the y values for the endpoints, the left endpoint, the right endpoint, and also the critical number, x equals e, we can find out what is the largest y value and the smallest y value on the interval x equals 1 to x equals e squared. The absolute maximum is at y equals 10 times e, because this is approximately 27.18, and it occurs at x equals e, so the largest y value for the function is 10 times e, and the absolute minimum will occur at the right endpoint. The y value was 0 whenever x was equal to e squared. So the absolute maximum occurred at the critical number, x equals e, and the absolute minimum occurred at x equals e squared, which was an endpoint. So be certain whenever you're comparing the y values that you also include the endpoints as well as the critical numbers to find out which is the largest and which is the smallest on that closed interval. So in the previous example, we talked about how to find the absolute maximum and absolute minimum on a closed interval. Suppose that we want to find the absolute maximum or an absolute minimum of a function that is continuous on an interval that is not closed. So you could have a half open or half closed interval or even an open interval. Notice that the extreme value theorem no longer applies because you cannot guarantee that there's an absolute maximum or an absolute minimum if the interval is not closed. So maybe the absolute maximum or the absolute minimum does not exist, or maybe possibly both don't exist. So let's look at example 5. Finding the absolute extrema on an open interval. Find the absolute maximum and absolute minimum values of the function f of x equals x cubed subtract 6x squared plus 9x plus 2 on the open interval negative infinity to infinity. So since we know absolute maximum and absolute minimum could occur at a critical point, let's find out the first derivative of f prime of x. So f of x was this polynomial, x cubed subtract 6x squared plus 9x plus 2. If you find the derivative using the sum and difference rules and also the power rule, f prime of x will be 3x squared subtract 6 times 2x plus 9 plus 0. And if you simplify, you'll have 3x squared subtract 12x plus 9. Notice that the derivative is a polynomial function, so f prime of x is undefined, never occurs, but we could have the slope of the tangent line be 0, and that is also a critical number, so f prime of x is equal to 0 gives you an equation to solve for x. 3x squared subtract 12x plus 9 equals 0. Notice that all three terms have a 3 in common, so you can factor it out as a greatest common factor, or GCF. So you have 3 on the outside, and now what's left over? You have an x squared from the first term, a minus 4x from the second term, and a plus 3 from the last term. So you have 3 times the quantity, 3x squared subtract 4x plus 3, all equal to 0. So now let's see if we can factor the trinomial that's left over inside the parentheses. You need to find two numbers that multiply to 3, and the same two numbers need to add to negative 4. Well, the two numbers at work are negative 3 and negative 1. So you'll have 3 times x minus 3 times x minus 1, all equals 0. So if you have a product that's equal to 0, one of the factors must be 0. 3 can't be 0, so x minus 3 equals 0 gives you x equals 3, and x minus 1 equals 0 gives you x equals 1. So in this case, we have two different critical numbers for the function. We have x equals 3 and x equals 1. So let's go ahead and find out what the y values are at the critical numbers. So if you have the critical number x equals 3, plug 3 back into the original function to find out the y value. F of 3 will be 3 to the third power, subtract 6 times 3 squared, plus 9 times 3 plus 2. If you simplify, you'll come up with the y value as 2. And now the other critical number, x equals 1, plug 1 back into the original function, and you'll have 1 cubed, subtract 6 times 1 squared, plus 9 times 1 plus 2, and that will come up with 6. So the y value is 6 whenever x equals 1. Now the point of this problem is, just because these are the two values that we actually plugged into the original function to find out the y values, doesn't mean that they're the absolute maximum or the absolute minimum. It doesn't mean that y equals 6 is the absolute maximum and y equals 2 is the absolute minimum, because the graph could rise even larger than 6, and the graph could fall even farther down than 2. So since we have an open interval from negative infinity to infinity, and there are no endpoints, we need to consider what is the behavior of the graph as x approaches infinity and as x approaches negative infinity. So let's construct a sign chart for f prime of x. We know that the sign chart tells us whether the original function is either increasing or decreasing on an open interval. So remember, if you want to construct a sign chart, you plot the critical numbers, x equals 1 and x equals 3, and so the critical numbers divide the number line up into 3 different pieces. You have x values that's less than 1, x values between 1 and 3, and you have x values that's greater than 3. So now choose test values on each of those intervals. Let's choose x equals 0 on the left side of 1. Let's choose x equals 2 between 1 and 3. And let's choose x equals 4 that is greater than 3. Now these test values go into the first derivative because we want to find out what is the sign of the derivative. If the derivative is positive, that means the original function f of x is increasing. And if the derivative is negative, then that means the original function f of x is decreasing. So x equals 0, plug that into the derivative. You have f prime of 0 is 3 times 0 minus 3 times 0 minus 1, and that will come up to be positive 9. So on this interval where x is less than 1, the original function is increasing because the derivative is positive. Now let's try x equals 2. If you plug 2 into the derivative, you'll have 3 times 2 minus 3 in parentheses times 2 minus 1 in parentheses. That comes out to be negative 3. So on this interval, the derivative is a negative number. That means the original function f of x is decreasing between x equals 1 and x equals 3. And now the last test value, x equals 4, f prime of 4 would be 3 times 4 minus 3 in parentheses times 4 minus 1 in parentheses. That comes up to be positive 9. So on this interval, the derivative is positive. That means f of x is increasing. So let's take a look at what happens on the ends of the graph. Whenever x is approaching infinity, the graph is increasing. So the graph will grow arbitrarily large, and so there won't be a largest y value. So there is no absolute maximum for this function. And on the other end of the graph, whenever x is approaching negative infinity, notice that the graph was increasing, and so the y values will grow arbitrarily more and more negative, and so there is no absolute minimum for this function. And remember that a polynomial function has no vertical asymptotes and no horizontal asymptotes, so the graph does not level out at the end of the graph either. So all we can say is that there is a local minimum, y equals 2, at the critical number x equals 3, and the local maximum is y equals 6, and it occurred at x equals 1, which was a critical number. We can't say that these are absolute maximum and an absolute minimum because the graph grows arbitrarily large as you go to the right, and the y values grow arbitrarily more and more negative as you go to the left on the graph. So there is no largest y value or smallest y value for the entire graph. So although there's not a method to find out the absolute maximum and absolute minimum as we found in the previous example, there is a procedure that can be used for searching for the absolute maximum and absolute minimum where the interval is not closed. So you have a half open or half closed or open interval for the function instead. So let's look at example 6. Finding the local and absolute extrema. Use the given information to find the local and absolute maximum and minimum values for the function f of x. So this time we don't have a formula for the function f of x, we just have information given in the problem. We know that the domain is negative infinity to infinity. We know the function f of x is continuous on the domain. And the limit as x approaches infinity or x approaches negative infinity of the function is 7. We have the values of the function. So if you plug x equals negative 5 into the function, the y value is 9. Whenever x is 8, the y value is 0. X is 21, the y value is 12. And we also have a sign chart for the first derivative. F prime of x is positive when x values are less than negative 5. The derivative is negative between x equals negative 5 and x equals 8. The derivative is positive between x equals 8 and x equals 21. And the derivative is negative again when x values are greater than 21. Also notice on the sign chart that f prime of x is 0 at x equals negative 5, and f prime of x is 0 at x equals 8, so that means the slope of the tangent line is 0 at negative 5 and x equals 8. And also notice that f prime of 21 is not defined. The nd means it's not defined, so that means the derivative does not have a value at x equals 21. So it means the slope of the tangent line is an undefined number. That means that the function could have a cusp, a corner, or a vertical tangent line at x equals 21. Notice in the sign chart for f prime of x, it shows us on what intervals f of x is increasing and decreasing. So f of x is increasing whenever the derivative is positive. So the function f of x is increasing from negative infinity to negative 5, and is also increasing between x equals 8 and x equals 21. The function f of x is decreasing when the derivative is negative. So f of x is decreasing between x equals negative 5 and x equals 8, and it's also decreasing whenever x values are greater than 21, so 21 to infinity. So this tells us from the sign chart that we have 3 different critical numbers. We have x equals negative 5, x equals 8, and x equals 21. Those are the values of x where the derivative is 0 or undefined. So we have 3 different x values that we want to find the y value for. We want to find the y values for each of these critical numbers. The y value for the critical number x equals negative 5 we can find from the table of values. Whenever x is negative 5, the function is 9. So the y value is 9 when x is negative 5. The y value at x equals 8 from this table of values was 0. So the y value is 0 when x equals 8. And the other critical number, x equals 21, if you plug that into the original function, you get 12. So the y value is 12 whenever x is equal to 21. So remember what we did in the last example. We know what the critical numbers are for this function, but we don't know what the endpoints are because we have an open interval from negative infinity to infinity for this example. So let's find out what is the behavior of the graph whenever x approaches infinity or as x approaches negative infinity. We were given a value of a limit in the problem. So whenever x approaches infinity, the limit of the function was 7. So that means the y values are approaching 7 whenever x is growing arbitrarily large. So that means that there's a horizontal asymptote y equals 7 for this function as x approaches infinity. And for the same reason, as x approaches negative infinity, we had the value of the limit was also 7 of the function. So the y values are approaching 7 whenever x is approaching the negative infinity. So on the left end of the graph, we also have a horizontal asymptote y equals 7. So what this means is that the graph does not grow arbitrarily large whenever x approaches infinity, and it does not go more and more negative whenever x approaches negative infinity. The y values are approaching 7 on the ends of the graph. So we can find the absolute maximum and absolute minimum now. The absolute maximum occurs at y equals 12. That's the largest y value that the graph will attain, and it occurs at x equals 21. And the absolute minimum will be y equals 0, and that occurred at the critical number x equals 8. So this finishes our video on finding the absolute maximum and absolute minimum values on an open interval. If you have any questions about any of the examples in this video, please let me know. Or if you have any questions while you work on the homework for this section, please let me know that as well. And I'll see you at the next video when we talk about an introduction to optimization problems.